All right. Hello, everyone. I hope you can all hear me and see me live from Switzerland. Welcome to this educational session on the challenges and opportunities of gas flow measurement and ventilator testing. So thank you so much for joining us today. It's a pleasure to have you here, and I truly appreciate you taking your time to attend. First, I would like to apologize that neither I nor my colleague Kerwin are able to be there with you in person. It's always easier in person. It's more like interactive. But unfortunately, Kerwin, as Jamie mentioned, had a unforeseen medical circumstances that didn't allow him to travel this week. And I'm currently at our headquarters in Switzerland, so I couldn't step in on site either. So, and a special thanks to Jamie and the MD publishing team for making this possible for me to deliver this session remotely today. I sincerely hope that you will still find the presentation valuable and informative, and I appreciate your understanding and participation despite the change in format here. So thanks again for being here, and let's get started. I hope you can see my screen. So again, my name is Daniel Benz. I'm the Managing Director of IMT Analytics US Sales and Service Entity. We are based in St. Petersburg, Florida. I'm originally from Switzerland, as you might hear on my German accent, but I've been living in Tampa Bay area for the past 2.5 years now. A little bit more about me. I'm an engineer by training. I've been working in the medical device industry for over 12 years. During that time, I've held different roles in technical support, technical training, customer service, and also management, both with a ventilator manufacturer and now with a test equipment company. So before we get started, I'll ask Jamie to take the results here of our little poll, just to better understand the room. So how many of you are currently involved in ventilator or anesthesia machine testing? If that applies to you, can you please go ahead and raise your hand? And maybe, Jamie, you can let me know how many more or less these are.
Yeah, about 11, Daniel.
All right. Great. How about maybe people that have never worked on a ventilator or anesthesia machine in their career so far?
Five.
All right. Okay, so thank you so much. So we have a pretty good mix here. So particularly for these of you that are new to this topic, if it's a little bit over your head, feel free to ask questions at any time. So just raise your hand, and then Jamie can probably interrupt me so that I can address this immediately. Of course, we will also have a Q&A session at the end of the presentation, so you can also note down your questions, and then I'm happy to answer them at the end. So, as mentioned in my introduction, I've spent the main part of my career in medical devices industry as technical support and training engineer for ventilators. And with that, I've personally faced challenges in gas flow measurement and ventilator testing. So since I've been focusing on the test equipment side, I see a lot of opportunities where well-designed products combined with the basic knowledge about gas flow measurement and ventilator testing can effectively help overcome these challenges. So based on our team's experience in the field and like frequently asked questions we have faced over the years, there are actually three main challenges we see and we want to discuss with you today. Challenge number one is that we often have complex and unclear measurement setups that we have to deal with. Then the second challenge we see is that it is difficult to ensure that your gas flow analyzer is set up correctly. And the third challenge we are going to discuss in this presentation is understanding the test sequence and the valid ranges for your measurements that you need to take defined by the ventilator manufacturer. So we will see in a little bit that this is sometimes not that easy as we would expect it to be. So while we go through these challenges, we'll keep this very general and generic. So this means we are not going to focus on a specific equipment or ventilator models. Our main aim here is to build your knowledge and that you all learn something new today. Okay, so then let's jump right into the topic with the challenge number 1. And here, what we often see is that measurement setups are quite complex, and ventilator manufacturers sometimes don't do a great job in explaining the setup with supporting pictures in their service manuals. And if they do so, it's most likely just for one specific testing device they once selected maybe years ago for some specific reason. So here on this picture, you can see an example for that. So here you can see 2 measurement setup pictures from a service manual of a ventilator manufacturer. Maybe some of you will recognize the ventilator here. The setup pictures themselves are actually pretty good, even though, for example, this teed-in pressure you can see here on this module here is kind of hard to see, right? The issue here is that the setup is quite complex and is based on this specific gas flow analyzer they selected for the picture. So as you can see, this one consists of multiple parts: the analyzer, a flow measurement module, a trigger cable around here, and also an O2 cell module, for example, over here in this picture. So with that, it makes it very specific to the gas flow analyzer that they are showing this picture. So what if you want to use a different analyzer? For example, the one here visible in the picture is a model that is no longer available exactly like that. So in such cases, the ventilator manufacturer just leaves it to you to figure out the correct setup, right? We have a second example on the next slide. Here, again, the setup picture is based on a specific brand and model of analyzer, but the picture doesn't clearly show, for example, here, which port of the flow analyzer you should use. In the previous picture, we had a nice like photograph, but here it's just a schematics and it's not 100% clear. So again, here, if you use a different analyzer, you'll need to figure it out yourself. Or sometimes you will see things like this one. This is a really good one. Here you just have one basic sentence to tee in a calibrated flow and volume analyzer into the patient circuit system, and you have to figure out completely by yourself how the setup has to look like. So, of course, we can't expect the ventilator manufacturers to add pictures for each and every analyzer available in the market, and also they wouldn't do that, right? So, therefore, it is critical, crucial for you to understand your gas flow analyzer. So, because depending on the analyzer you use, your measurement setup can look very different. For example, the setup we see on the picture here on the left-hand side of the screen, we've seen that a little earlier, can look as simple as in the picture on the right side for a different analyzer. So important for you is to make sure you know how your gas flow analyzer measures relevant parameters and check the user manual for setup specific information. It is really crucial to understand, for example, what is being measured in the main flow channel of your analyzer, and maybe even more important, what is not. So maybe sometimes you have to tee in some different things. So be aware that the wrong setup can lead to significant measurement errors. For example, if you don't tee in oxygen measurement, depending on what you measure, your flow rates can be quite off. The opportunity for test equipment manufacturers is to design the device in a way that it allows simple setups. So when you choose a gas flow analyzer, we always recommend you to select one that is designed with a focus on allowing simple measurement setups. with that, such devices are usually called all-in-one devices, where all the relevant parameters are being measured inside a single flow channel. So this is an example of a gas flow analyzer in the schematics here. This is the ventilator, and all-in-one devices, they just measure everything inside the one flow channel. So with that, the setup is usually very simple. So you just have to connect the Y piece of the ventilator circuit system on one side of the flow analyzer and the test lung on the other side, and everything else is measured inside the flow channel of the gas flow analyzer. So this helps to reduce the risk of setup-based measurement errors. Does anyone have any questions so far? Before I go ahead.
We're good to go.
No questions?
No questions yet.
Okay, all right, thank you. Okay, so the second challenge we often see is to set up the gas flow analyzer correctly for the specific measurement application. We're going to spend most of our time with this challenge as it is the most important one and needs some in-depth background knowledge to understand what we are talking about. So the most important settings on gas flow analyzers and ventilator testers are gas type and gas standard. So maybe the ones of you that have already tested ventilators, they have at least heard these terms. So these two settings are crucial for all flow and volume measurements. This third setting we are going to talk about is actually a set of settings. It's the trigger settings. They are relevant when we want to measure so-called breath-based parameters, such as, for example, a PEEP pressure, respiratory rate, or tidal volume. And last but not least, the measurement parameters themselves. Gas flow analyzers can measure many different parameters in different units of measurements. So we must ensure that we look at the right parameter and we have it set up with the correct unit of measure. So let's dive a little bit deeper here and first talk about the gas type and gas standard settings. So why do we need to set a gas type and gas standard on our flow analyzers? The reason behind is that volume that is occupied by gas is dependent on several factors. So let's assume we can capture a certain volume of just room air in the meeting room you're in right now, and in a container that has a movable lid. And let's call that V0. That's our volume, initial volume V0. So what happens if I would increase the temperature of that volume of trapped air? The answer is it's going to expand. Because of the movable lid, it can expand and it's going to occupy a larger volume than our initial gas. The same applies when we increase the humidity of the gas. It's going to expand as well. On the other hand, I think you all know that we can put gas under pressure and compress it, so the volume decreases. And as a last example, if we increase the level of oxygen in our gas mix, so our room air has 21% more or less oxygen concentration. So if we would add more oxygen to the gas mix, it would expand as well. So this means that the same number of gas molecules occupy a different amount of volume depending on gas conditions like temperature and humidity, and characteristics, for example, how much oxygen is in the mix. Because of that, gas flow measurement is kind of complex. So the gas flow analyzers need to know many different parameters to finally calculate flow and volume. So there's just a whole list. Don't worry, we'll not go through all of them, but the first three ones are the gas density, viscosity, and the so-called viscosity coefficient. So we are not going to set these individually. They are actually related to the gas characteristics and are defined with a setting we call gas type. you will see that setting on any gas flow analyzer. So we need to tell the device if we want to measure flow or volume, for example, of air, oxygen, or a mix of air and oxygen, but we could also say CO2. But we need to tell the gas flow analyzer what gas flow we are going to measure. Other parameters, like all the others on the list here in this example, are being measured by the gas flow analyzer. For example, gas temperature, the gas pressure, and the oxygen concentration. So with all these set and measured values, the gas flow analyzer can then calculate the actual flow rate passing through the device. And as we all know, volume is just flow over time. So the same applies for the volume. And we consider this process gas flow measurement. In order to understand the meaning of a gas standard, we first need to understand the separation between gas flow measurement and gas flow displaying. So as we have seen in the previous slide, the gas flow measurement is actually based on the actual gas conditions. This is typically called the gas standard ATP, that stands for actual temperature and pressure. So, but then in order to make flow rates comparable and independent from our gas conditions, the flow rate can then be converted by the gas flow analyzer, and the result can be displayed in a different gas standard at standardized gas conditions. For example, how much of flow would that be if the gas was 98 degrees Fahrenheit and 100% humid, even if it's actually not, when we measure it with the analyzer. And this conversion, or the value that we display, is considered gas flow displaying. So this is really something we have to separate, what we measure and what we display. So that was a bit of a background theory, but now you might ask, why do we need to care about that, right? So let me show you the practical part about it. So what you can see here is a typical ventilator setup on a patient. We have the ventilator with a circuit system. So we have an inspiratory limb, which is typically humidified and also heated with a heating line inside of our inspiratory limb. Then we have the Y piece where our patient interface is connected. Here it's just a mask, but it could also be a tubus. And then we have a second limb for the exhaled gas that actually goes back to the ventilator, to the exhalation port. So let's assume in this specific example here that this ventilator delivers a volume of exactly 500 milliliters measured at the output of the ventilator by its internal sensors. And let's assume that this ventilator takes air from a compressor system, so it is going to be pretty dry. And let's assume that it has a temperature of 21 degrees Celsius. What happens to that volume of gas while it travels along the inspiratory limb here until it actually reaches the patient? So because we have a humidifier and a heated wire, a heated limb, the gas temperature and humidity is going to increase. And what is the consequence based on what we've learned earlier in our earlier slides? The volume is going to increase as well. So this means with our example here, the volume that actually reaches the patient is no longer the 500 milliliters that the ventilator delivered, but it's now approximately 560 milliliters, because the gas temperature at the Y piece is 37 degrees Celsius and the gas humidity is 100%. So what ventilator manufacturers usually do is that they compensate for that with their setting and monitoring with the values on their devices, as this can all be calculated through gas standard conversion. So in our example here, the setting and monitoring value on the ventilator would typically see in such a situation is not the 500 ml delivered to the circuit system, but 560 milliliters that is actually going to end up being delivered to the patient. because they know that this is going to happen in a real life scenario. Has 37 degrees Celsius and also is also the typical body temperature and the gas condition. So the gas condition at this temperature and 100% humidity is typically called the BTPS standards. That stands for body temperature and pressure saturated. Therefore, many ventilators display, particularly ICU ventilators, display settings and measurements in the BTPS gas standard to reflect volumes actually reaching the patient. So what is the issue here? Well, when we test such a ventilator with our gas flow analyzer, the setup typically looks different, more like as we can see on this slide here. In such a situation, it can then easily happen that we have a setting on our ventilator for tidal volume of 560 milliliters, but then with our gas flow analyzer, we just measure 500 milliliters. So how can that be? So, well, assuming that the ventilator setting is using the gas standard BTPS means that is going to under-deliver in volume, as we have learned earlier. So even though we set 560, it's going to deliver just about 500 milliliters because it considers an increase of the volume in the patient circuit system caused by an increase of the gas temperature and humidity as it travels along the circuit until it reaches the patient. However, unlike in our previously discussed patient real-life scenario, in our test setup, we typically don't have a humidifier and a heated lamp. So that means that our gas condition is not going to change. So we don't have the increase in temperature and in humidity. So that means the same 500 mLs that are going to be delivered by the ventilators are going to end up on our measurement device, on our gas flow analyzer. And if that gas flow analyzer is then set to gas standard ATP, it's only going to measure 500 milliliters as a tidal volume. So what we do in this example here is we compare different volumes in different gas standards, BTPS on the ventilator and ATP on our gas flow analyzer. And as you can see, this can lead to significant errors. So how do gas flow analyzers tackle this problem? Well, they let you display flow and volume in different gas standards. And the only thing you really need to remember is that the gas standard setting on your gas flow analyzer must always match the gas standard used by the device under test, typically your ventilator or anesthesia machine. Different ventilators manufacturers, they use different gas standards. So the most common ones are called SDP and BTPS. BTPS usually for ICU vents, and SDP more for like BiPAP machines and more basic ventilators. So you need to figure out what gas standard is used by the device under test and then set the same gas standard on your gas flow analyzer. On all gas flow analyzers out there in the field, you have different ones to choose from. So you will find the ones you need. Most vent manufacturers specify the gas standard used in their technical documentation. Otherwise, they will be able to tell you when you ask them. Okay, back to our example, because if we set the same gas standard, then we also compare the same values with each other. So even though our gas flow analyzer then measures just the 500 ml, if we set the gas flow analyzer to BTPS gas standard, the same standard used by our ventilator, then our displayed value is also going to be 560 ml as the setting on the ventilator. Because now we are comparing apples with apples. Or maybe these guys here, probably more banana with banana. All right. So that was actually what I wanted to show you about gas type and gas standard, which is really important, particularly the gas standard, something that a lot of people are not aware of, so that we hear from phone calls we have or tech support cases. make sure that this is always set to the one used by your device on the test. Before we go ahead with the next setting, Jamie, are there any questions so far?
Any questions so far for Daniel? Not yet.
All right, then let me go ahead. So the other critical settings of gas flow analyzers you probably have heard already are trigger settings. So as most of you will know, gas flow analyzers do not only measure flow rates, volume and pressure, but they can also interpret the flow and pressure waveforms and then calculate so-called breath-based parameters. If you are involved in ventilator testing, I'm sure you've seen test setups where you actually need to run a ventilation on a test lung and then verify things like tidal volumes, respiratory rate, or for example, a peak inspiratory pressure. So to measure and then calculate these breath-based parameters, the gas flow analyzer needs to be able to determine the breath phases, means to know when a new breath phase starts and when it transitions from inhalation to exhalation. In a typical testing application where a ventilator is connected to your gas flow analyzer and test lung, you will see flow and pressure waveforms. They will probably look like as they are displayed here on this slide. So trigger settings are used by the gas flow analyzer to identify the start of an inspiration phase and then the transition from inspiration to exhalation. In most analyzers, you will see, actually always you see two sets of settings. One is most likely called the start trigger, and the other one is most likely called the stop trigger or the end trigger. So this always relates to the inspiratory phase. The start trigger is used to determine the start of a new inspiration, which means a new breath. And then the stop or end trigger is used to determine when it transitions from inspiration to exhalation. And as mentioned earlier, the triggers are necessary for the analyzer to calculate the so-called breath-based parameters, all the things that are based on our actual breath. So for example, volumes like tidal volumes, inspiratory, expiratory tidal volume, a rate, an I/E ratio, or something called PEEP you might have heard about. Without triggers, the gas flow analyzer can't calculate and measure these parameters. And typically, if they can't, they won't display anything or just say something like no trigger, where you should see the measurement. And most gas flow analyzers also have like an indicator on the display that shows you each time when the analyzer is triggering. For example, on IMT Analytics Analyzer, there's like a T symbol flashing on the display whenever a trigger is being detected. So if you do ventilator testing and you need to measure these breath-based parameters and you can't see this indicator or you can't see any measurements of your breath-based parameters, this means that your trigger settings are most likely not suitable for your current application. By the way, the term trigger setting is also used by the ventilators themselves, but this is something completely different. So it should not be confused with trigger settings on the ventilator. So some people sometimes are confusing these two things. So we have just learned that we need triggers to even be able to measure breath-based parameters. But even if our analyzer is triggering, inappropriately set triggers for our specific application can also have impact on the accuracy of the calculated breath-based parameters. Because, for example, the inspiratory tidal volume is calculated by the analyzer by mathematically integrating the flow from the start trigger to the end trigger of an inspiration phase. So think of it as this is the flow waveform and our volume is actually the area underneath the curve here, which is shaded here. And our trigger settings should tell us when an inspiration phase starts and when it ends. So in an ideal world, it captures the exact start, which is actually here at this position, and the exact end, which would be right here when the flow goes negative. And if our trigger settings timing is off, as you can see on this slide, then it has impact on our calculated values. Because, for example, this start trigger is delayed a little bit, so we are missing the first part of our volume calculation here. And on the other hand, because our end trigger is also too late, we are considering part of the negative flow here in our volume calculation for the inspiratory tidal volume. So that means in this specific example, our calculated VTI will be significantly too low. So this means we need triggers, and we also need them to be timed as close as possible to the real breath phase transitions. So let's see how we can do that by using trigger settings of our gas flow analyzers. So trigger settings are, when you see them, when you open the menu on your gas flow analyzers, you will typically see three main parameters. The first one is a trigger source. Then we have something called a trigger signal and a trigger level. So the trigger source defines the physical interface for the trigger. This could be, for example, a measurement on in one of your flow channels of your device, but it could also be a pressure port of the analyzer. Most analyzers also offer the option to use an external digital trigger signal as a trigger source. So we'll talk about that in just a bit. Then the trigger signal defines which signal shall be used for triggering. So here you can typically choose between the pressure waveform or the flow waveform of your gas flow analyzer. For example, if you have an analyzer that measures pressure inside the flow channel and you want to use that signal as trigger source, then you can set up your trigger source to be the flow channel and then the signal to be the pressure in the flow channel. And finally, the trigger level, number 3 here, defines the threshold value on this flow signal or pressure signal for the trigger to be activated. In addition to the actual value, when it should trigger, we will also need to define whether the trigger shall be activated when the threshold is reached on a rising edge of the signal or a falling edge of the signal. So you will find such trigger settings on all gas flow analyzers. But it might very well be that you have never touched them, and more about that in just a minute. So how do we choose the correct settings here, right? So first of all, we need to understand what a good trigger signal is. And the answer is quite simple. A good trigger signal allows us to set trigger levels to be as close as possible to the timing of our real breath phases. But the question is, how do we determine the best source, signal, and levels? And this might be challenging based on your application. There are some basics that I would like to share with you in form of a little cookbook here. So first of all, there's something called an external trigger signal. And this external trigger signal is provided by the ventilator. So some ventilators have an output that says trigger, and then it creates a digital signal whenever the breath phase starts and when it changes to exhalation. So because the ventilator controls the ventilation and can tell the analyzers through the digital signal when the transition from one breath phase to the other happens, this is the most accurate we can go, all right? The issue is that not many ventilators actually provide such a signal. So typically in the field, I've seen the Philips V60 and maybe one other, I can't remember which brand it was, but most of them don't. Additionally, trigger cable is just an additional part in your setup, so it makes your setup more complex. And therefore, the more common way is to use the pressure or flow signal measured by your gas flow analyzer. So the question is, which waveform do we choose as a trigger signal? So the most important thing here is that we choose the waveform with the fastest significant changes around the real breath phase transitions. So this means where we have the steepest signal slopes. So if we take a look at these examples here, so we have a pressure waveform up here, and we have a flow waveform down here. The dotted lines indicate the actual real breath phase transitions. So in this example, we would choose the flow signal over the pressure signal because the flow signal has very significant and rapid changes in the signal when we have our actual real breath phase transitions. The pressure signal here, it's quite good at the end of the inspiration phase, but here at the start of the inspiration phase, this signal, we call that a slow signal. It has a very flat, kind of a flatter waveform, a flatter curve. So that means that the pressure signal in this example is rising slowly and therefore not sufficient as a trigger signal. For the trigger levels, means the threshold level for the trigger, it's always a bit of a trade-off. On one hand, we want to get as close as possible to the signal baseline to capture the start of the breath phase as accurately as possible. Because the more delayed we are, the more inaccurate our breath phase parameters measurements are going to be. We've seen that in our earlier example. So here we have on the left side, a flow waveform, which is not that steep as in our example on the right side. And if we have our levels here with the dotted line here, the orange line, oops, sorry. If we have our threshold, for example, here, then we are missing a little bit of our start of our first phase here. And also we are a little bit delayed at the end of the inspiration phase. So our measurements are gonna be a little bit off. However, we also don't want to go too close to the baseline of the signal, because if we go too close, then just little signal noise can create false triggering. So that's why we want to get a little bit away from the baseline of the signal as well. As we have learned earlier, if we have fast signals with a steep slope, then the exact trigger level becomes a little less relevant as the signal is that fast. So for example, in these two waveforms, we see the same levels for the trigger with these orange dotted lines here. And you see these arrows here marked when the trigger hits. And you can see, because this signal on the right side has faster signal slopes, our actual detection of the breath phase is far closer to the real breath phase, as in this example on the left side, where we have slower signals. So that all sounds a little bit challenging, right? So quick question for the room, and Jamie, you can probably let me know the result. How many of the ones of you that are involved in ventilator testing have ever touched these settings on your gas flow analyzer?
We have one rock star in the room that has.
Okay, and that doesn't surprise me, because the good news is the most modern gas flow analyzers have default trigger sets for example, adult, pediatric applications and high frequency ventilator testing. And these triggers will work well in, I would say, 90 to 95% of your applications. It's specifically always where you have a positive and negative flow through the flow channel of your analyzer. And in most ventilator testing applications, you will have a setup that looks a little bit like this one here. So you have your ventilator, you have a dual limb circuit with an inspiratory and expiratory limb, you have your Y piece, and then you connect your gas flow analyzer after the Y piece and a test lung after your gas flow analyzer. So in such an application, you will always have like a positive flow through the gas flow analyzer in inspiratory phase, and then all the gas goes back through your gas flow analyzer in a negative flow through your, or the opposite direction, through your gas flow analyzer back to the ventilator. And this means that we will have signals, typically like with ventilators, you will hear the terms volume controlled and pressure controlled ventilation. So it's not that important to understand these details, but the key is in both these different modes of ventilation, your flow waveform will typically have these steep rising and falling edges we are looking for at the start and the end of an inspiration phase. And the other good thing about that is they typically don't depend on the setting of the ventilator. So for example, if you have a ventilator where you set a tidal volume of 500 milliliters, and if you set that to 800 milliliters, the thing is the flow waveform here is going to change, but the fact that it starts at 0 and rises up at the start of an inspiratory phase and then goes negative at the end of an inspiratory phase when the exhalation phase starts doesn't change. And the same applies for volume controlled ventilation, whether you have like a pressure support of 10, 15 or 20 centimeters of water pressure doesn't change the fact that your flow is first going positive during inspiratory phase and then negative during exhalation phase. So this is why the flow signal in the flow channel with a start trigger level that is kind of a low positive number on a rising edge and a low negative, and the stop trigger a low negative number on a falling edge of the signal typically work perfectly fine. And this is also why these settings you can see here on the slides or very similar ones are typically the default trigger settings of your gas flow analyzers. All of them have pretty much the same settings as default settings. That's most likely why you have never had to touch them. But, and now we need to talk a little bit more in detail, because I also want to let you know that sometimes you will find applications where it matters. And then you need to understand how you can set the trigger settings. So in this example here, we have a BiPAP ventilation. And in such test setups, typically the ventilator delivers with the pressure gas to the test lung. And then that gas actually leaves the test lung through a leakage in front of the gas flow analyzer on the side of the test lung. And because of that, we will not have any negative flow through the gas flow analyzer. And in such a situation, you will see your flow waveform looks something like that, as we can see here on this slide. And here we don't have our signal changes that we want. So we cannot really trigger on the flow waveform. However, the pressure waveform has these nice slopes here actually. And typically in such a situation with BiPAP ventilators, you would then select, choose the pressure waveform. And you would then set the start trigger on the pressure waveform, like here, for example, when it rises up. Typically, they call these two pressure levels IPAP and EPAP. So you will have your start trigger here, your end trigger here, and that is going to work perfectly fine. So let's say you have the settings IPAP 6 and EPAP 2 centimeters, then you probably have your start trigger at 3 and your end trigger here at 5. And this is going to work well. However, let's say you have to change your settings on the BiPAP machine, and then you change IPAP to 8 and EPAP to 4 instead of 6 and 2, then your gas flow analyzer might do this and just say, well, not measuring anymore. So the reason here is that the settings of the triggers are now dependent of our settings of the ventilator. So if we take a look at the graphics with our previous settings, now our waveform is shifted up and it's no longer going to trigger because that lower level here is not going to be reached anymore. So here we would have to, based on the settings of the ventilator, we would have to correct the settings of our triggers to actually have measurements again. So long story short, particularly in BiPAP applications, you will have to understand your trigger settings and set them accordingly. So that was it about the trigger settings. So the last thing on challenge number 2 here is actually on the setting side is the settings of your values you're looking at. So gas flow analyzers and ventilators, they have different terms and modes they use for performance verifications. For example, one ventilator might use the term P peak for the maximum pressure during the inspiratory phase, while another one uses the term PIP, which stands for peak inspiratory pressure. But this is actually the exact same thing. So that's why gas flow analyzers can typically measure and calculate more than 25 different parameters. And usually they can display them in multiple different units. For example, pressure in centimeters of water pressure, millibar or Pascal. So it's important that we understand which value that we need to look at so that we know what terminology our gas flow analyzer is using and our ventilator so that we can set up the right value on our monitoring view of our gas flow analyzer and also have it set up in the right unit of measurement. So otherwise we compare probably different units or different parameters, and we can have different readings. So what are the opportunities posed by these challenges to set up your gas flow analyzer correctly? First of all, if your gas flow analyzer offers this feature, it's highly recommended to use, to create and use profile for your specific applications. On modern gas flow analyzers, you can create profiles to save all the critical settings we have discussed earlier. So the gas type, gas standard, your trigger settings, and your measurement screens customizations with your units of measurement, for example. So this is actually by working with profiles, when you save them, then you can just next time when you have the same application, you can just load that profile and everything is set up correctly again. So this is a really important help to minimize the risk of inappropriate settings and reading errors. Secondly, most modern gas flow analyzers offer valuable aids and automation features helping you to find suitable trigger settings for your specific application. So check if your gas flow analyzer has features like on-device waveform analysis, making it easy to determine the best trigger signal and like trigger level, or graphical trigger settings indicators, as you can see on the screen here, to help you better understand what impact your settings changes are going to have on your waveform and where you're going to measure the levels. And the latest gas flow analyzers even offer smart automatic trigger detection. So they analyze the flow and pressure waveform automatically in real time and then determine optimal trigger settings for you and set them accordingly. So just imagine how helpful that will be in a situation we discussed earlier with the BiPAP ventilator, where we have to adjust our trigger levels based on the settings on the ventilator. So these features help you find the best possible trigger settings and allowing the highest accuracy in measuring breath-based parameters. All right, I'm going to shift gears a little bit and talk about the last challenge I wanted to discuss with you, and this is understanding the sequences and valid ranges defined by the manufacturers. Here is an example. I don't expect you to be able to read all that, but this is an extract from a service manual where it asks you to calibrate different pressure scale points. So basically, we need to set a certain pressure on the ventilator and then check if the measured pressure by the analyzer and the ventilator are within an acceptable range. That sounds very easy, right? But in this example, it turns out to be a bit tricky, and the instructions provided by the manufacturer are quite difficult to understand. So let's have a closer look. First, we need to read some values displayed on the ventilator at 0 pressure. Then we need to set the pressure to 10, 35, and 60, and actually compare what we measure with our gas flow analyzer. But here, the thing is, we need to calculate our limits ourselves. So they they saw that this is quite complex, so they also added in their appendix kind of a calculation example. And as you can see, it's not that easy. So we detailed it a little bit for you. So per scale point, they want you to go through 9 steps of reading values, calculating values, and then finally judge if the calculated values are within the calculated ranges. Of course, it's important to be trained on the procedures of ventilators you are testing, but procedures as the one we have just discussed as an example can be very cumbersome and prone to errors. This is the second example. I'm not going to go into details and save a little bit time here, but this is quite of the same thing here, just with flow measurements. So that happens very often. So the ones of you, for example, that have tested Philips V60 vents, they're going to see that that looks pretty familiar. So the last opportunity here I would like to discuss with you is a feature that is offered by kind of state-of-the-art gas flow analyzers, which actually not only addresses this challenge, but all the challenges we have discussed. It's something called ready-to-use specific testing apps or test sequences that actually guide you through the performance verification as per the manufacturer specification. So testing apps can run on the device, and then they can actually, they can take measurement. They can guide you, first of all, through the whole procedure. So they can show you how you have to set up your ventilator, like in this screenshot you can see here, and your gas flow analyzer. And then they take and interpret measurement automatically. So because it's like a coded version of the service manual, it knows what measurements we have to take, and it can calculate the ranges and give you pass-fail results if needed right there on the screen. And also, these applications and test sequence typically create test reports at the end, including all the results that can then be saved and exported as a PDF files. So beside the fact that it helps to make workflows more efficient, and it also eliminates the risk of measurement and transcription errors. And it also ensures that all the device settings, such as gas type, gas standard, and trigger settings, are correct for the device under test, because this is already programmed into these sequences. Okay, so key takeaways from this session. Number one is that you need to understand the features of your gas flow analyzers. Being aware what is measured in the flow channels or the different ports is really important, so that you can make sure that you have the correct setup for a specific application. Number two is pay special attention to the setup of the analyzer for your specific device under test. As you've learned in this session, inadequate settings can have a significant impact. So if there is one single thing I would like you to remember from this session, is that your gas flow analyzer need to be set to the same gas standards used by the ventilator. And last but not least, also take advantage of the advanced features of your current or your future gas flow analyzer that can help you reduce the risk of insufficient settings and measurement errors. We see a lot of people, they have all these tools, but sometimes they don't use it because they probably don't read the manual or don't really take the time to figure out what they can do with these devices. And this is really worth the time. It's going to save you time, and it's going to help you reduce errors. Okay, that wraps things up that I wanted to discuss with you today. So thank you again for your participation. We are at table 35. Our devices are there. We are actually not there, unfortunately, as I already mentioned, but you can have a look at the devices there. You can play around with them. There's also a QR code you can scan to get in touch with us. And our partner BC Group is located at table 65. They are one of our distributors, and they're happy to give you a demo or answer any questions about our products that you might have. So with that, I know we are already at time, but if there are any questions, please let Jamie know. Otherwise, again, there is a QR code at our table. If you scan that, please get in touch with us. We would really appreciate that. Thank you once again.
And your fantastic presentation.